Hello everyone. In this video, we are going to solve problem 3.11 from Jackson's Classical Electrodynamics textbook. Problem states, modified Bessel-Fourier series on interval from 0 to a for an arbitrary function can be based on following two homogeneous boundary conditions. The first condition restricts nu, while the second condition yields eigenvalues k. In part A, we have to show that the Bessel functions of different eigenvalues are orthogonal in the usual way, while in the part B, we have to find normalization integral and show that an arbitrary function can be expanded in the modified Bessel-Fourier series with coefficients given by expression beneath. We start with proof that set of Bessel functions S is orthogonal with respect to usual inner product given by following expression. We are starting from the Bessel differential equation satisfied by nth function from set S. Let us multiply both sides of previous equation with this term and integrate both sides of equation with respect to rho on interval from 0 to a. In the next step, we are going to solve integral I1 by using integration by parts. By applying boundary conditions given in the problem, we can evaluate following two terms. This yields that integral I1 can be written in form. By substitution of expression for I1 in expression 1, we can obtain this expression right here. And since indices n and n prime were arbitrary, we can interchange indices n to n prime and n prime to n in 2 to obtain symmetric expression of expression 2. By subtracting expression 3 from expression 2, we can obtain following expression. If eigenvalues of corresponding to nth and nth prime function from set S are distinct, then nth and nth prime function from set S are orthogonal, which was to be demonstrated. Normalization integral of function f can be calculated as inner product of function f with itself. Hence, we have to evaluate integral on this slide. Integration by parts yields this expression for integral I2. In order to solve integral I3, we have to recall Bessel differential equation and express term under integral I3 in this form. While integral I3 can be expressed in following form. Third integral on right hand side is trivial, while first integral on right hand side of 4 can be solved by using integration by parts, with u and dv given in between vertical lines. By substitution of evaluated integrals in 4, we have following expression for I3, and substitution of integral I3 in expression for integral I2 yields final expression for integral I2. Normalization integral I is now given by this expression, and now we can calculate we can sum up what we have calculated in parts A and B so far in this orthogonality relation involving Kronecker delta function. Considering that set S is complete, arbitrary square integrable function on interval from 0 to a can be expanded in modified Bessel-Fourier series with coefficients calculated by using orthogonality relations for functions from set S. And here is the calculation of these coefficients. And after evaluating sum which involves Kronecker delta function, we will obtain isolated expression for nth prime coefficient and by interchanging dummy index n prime to n, we'll obtain desired expression.